All right, so last thing that we should look at in terms of atomic structure would be the electron configuration. The orbital diagrams are cute. They give me a visual of where all the electrons are located, how they're distributed. What I really like about the orbital diagram is that it gives you kind of that snapshot of like the P's and the D's. Are these electrons paired? Are they unpaired? And what we're going to find in the next lecture guide is that having paired electrons or unpaired electrons can affect some of the properties of that element. And so I like that about the orbital diagram. But to be honest, I don't want to always draw out a bunch of stinking boxes. It's cute when the boxes are already drawn for me, but what if I get to, element number 50 or something? Do I want to look at 25 boxes? Not really. So often we condense that into an electron configuration. Electron configurations are just a shorthand way of saying most of the information that you see in an orbital diagram. The order that these orbitals fill can be predicted by looking at the periodic table. And again, I'm hoping that your teacher showed this to you last year. If you ever have to do anything that deals with orbital diagrams and electron configurations, the very first thing I would do is mark up your periodic table like this. Going down the side, if your periodic table doesn't already have the rows numbered, I would do that. So, you could do this when you get to the AP test and you got your periodic table and you see, whoa, this is an atomic structure question, an electron configuration question. Start going to town. Mark up that periodic table. Label down the side. The periods, the rows going across, should go 1 through 7, representing the 7 energy levels. Maybe someday there will be an 8th. Now, going across, there is a reason why we have 2 groups that are kind of together like this. Group 1, the alkali metals, and Group 2, the alkaline earths. This is called the S block. So I would totally write that in there, an S. That's the S block. A couple things that are interesting. Whoever designed this periodic table, Moseley, Mendeleev, old farts, those guys are smart. I like this. The S block goes across 2 elements to represent the 2 electrons that can fill an S orbital. The other thing that I like is that the S orbitals are found in every energy level. There's a 1s, first energy level, S orbital, 2s, 3s, and so on. Now for electron purposes, I kind of like to write in a little ghost helium. So I get it. Helium is not an alkaline earth metal. I'm just making like a little pretend helium, a little ghost helium. Here's the problem. Helium is a noble gas. It's a non-reactive gas. So that's why on the periodic table, helium is listed with neon and argon and so forth. They have similar properties. The problem is when you start looking at atomic structure, helium looks a lot more like beryllium and magnesium. He fills S orbitals with 2 electrons. So sometimes you might have a periodic table that may even like color helium different, and that's why on this periodic table they kind of have it colored different. For electron purposes, I'm going to pretend that helium is next to hydrogen, and so on. So every energy level has an S orbital, and it can fill with 2 electrons. So for electron purposes, we're going to pretend that this is not there. Helium is over by hydrogen. Over on the right-hand side, we're going to label this the P block. A couple things that I like about this. If I count across 1, 2, 3, 4, 5, 6, the P block goes across 6 elements to represent the fact that 6 electrons can fill the P orbitals. Wow, this is fascinating. The other thing, this is even better. I would mark this in. There is no such thing as a 1p. If we pretend that helium is not here, pretend that helium's over in the S block, then there is no element in this 1p area because there are no p orbitals in the first energy level. They're not found till the second. So I always do this. Second energy level. I follow this across and I write it in 2, 3, 4, 5, 6, 7. And that reminds me that there are no p electrons in the first energy level. Sometimes by accident, people will call this first row 1p. Because they'll be like, oh, it's the first row of the p block. Ugh. Yeah, but it's not really the first energy level. In the center of the periodic table, we have the D block. The D block goes across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements to represent the fact that 10 electrons can fill d orbitals. This is just brilliant. Now watch it. Well, it gets kind of better. As long as we add one little thing in. Do you remember that little snafu about how the 4s orbital is actually a little bit lower in energy than the 3ds? Those d orbitals, there are 5 of them. They're kind of high energy. So even though like the electrons are a little bit closer to the nucleus because they're in the third energy level, being that they're d orbitals, they carry more energy than the 4s. Here's how we can never get this wrong. When you get to the D block, the D's don't start till the third energy level. Write that in. This is the 3D, 4D, 5D, 6D. Write it in. The D's don't start till the third. Because now watch what happens. All you have to do is follow across on the periodic table, and it will tell you the order that the orbitals fill. You don't have to memorize any of this. The first orbital that gets filled is the 1s. It gets filled with 2 electrons. That's it for the first energy level. Then you go to the second energy level. You'll fill the 2s with 2 electrons. Then you move across to the 2p. The 2p can have up to 6. That's it for the second energy level. Next, we have the third energy level. The s orbital comes first with 2 electrons. I follow across. Then I would fill the 3p with 6. And now watch what happens. In order of increasing energy, the next orbital filled is the 4s. And then I go get the 3ds. So they kind of fill out of order, what you might not expect. But if you mark up your periodic table, all you do is follow across the rows, and it totally tells you that. This is the 4th energy level, S block. Then I go to the 3rd energy level to get those Ds. And then it's back to the 4th energy level for the Ps. Next orbital fill is the 5s with 2. Then it's the 4d. It's always like that. The d orbitals fill 1 less than what you might expect. So it's the 4d with 10. Then I go back to the 5th energy level and pick up the p orbitals, 6 electrons. Next is the 6s with 2 electrons. And now watch what happens. Now in first year chem, you probably didn't do electron configurations for elements that get close to this 5D range. Some periodic tables will write this a little different. Look closely at what periodic table you're using. And that reminds me, I should just kind of peek at the periodic table on the AP test. Yep, it's like this. Okay, so technically lanthanum is number 57. And then next door, we've got, oh, funky, 72? Element 72? Element number 72 is hafnium. Well, where did the rest of them go? They're down on the bottom. Here's 58 through 71. They're down in what we call the F block, the mysterious F block, which in first year chem maybe you mentioned, but then your teacher was probably like, yeah, we're not going to deal with those. They're unstable, they're radioactive, some of them are synthetic, many of them are synthetic. So like for purposes on the periodic table, they do kind of have similar properties. They're pulled out, but they're also pulled out into this F block because they fill F orbitals. Now watch what happens. We said that there are 7 F orbitals. Each can hold 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What do you know? The F block goes across 14 elements to represent the fact that 14 electrons can fill F orbitals. Wow, that's crazy. Now the same thing's going to happen down when we hit like 7s. We hit 7s, and then if you look closely at your periodic table, this is number 89. That's an 8. And then if you're like, where's number 90? Where's thorium? Oh, he's way down on the bottom because he fills F orbitals. And then this is going to go all the way across, wow, to element 103. And then this will pick up again at element 104. Crazy. And we'll do an electron configuration for one of these big guys in a minute. And again, would you find one of these on the AP test? Possibly. But when we get to these F orbitals, again, these elements are all rare. They're synthetic or radioactive, unstable. So this wouldn't be the first choice of an element. But I mean, they could throw something at you in a multiple choice question. Okay, so here's what I do. I see that I'm doing electron configurations. It takes me like, I don't know, 10 seconds to mark up my periodic table. Well, maybe not 10, but it's quick. All I gotta do is number it 1 through 7. It's already numbered on this periodic table. Then I label this S. I label this P, D, F. Then I start numbering the rest of the blocks. There's an S orbital in every energy level, and I'll pretend that this is helium so that I don't have to deal with them over here. When I number the P block, the P's don't start till the second. 4, 5, 6, 7. When I number the D block, the D's don't start till the third. 3, 4, 5, 6. And the F orbitals aren't found until the 4th energy level. So this is going to be numbered as the 4F and the 5F. Done. And now I've got the order that these orbitals will fill, as long as I know how to use my periodic table. Okay, so first I need to find my element, fluorine. Fluorine is element number 9. There he is. So you've got to start with element 1, and you just work your way to the element you're looking for. I'm going to need to start with the first electron. First and second electrons will go in the S. That's it for the first energy level, 1s2. I go to the second energy level. Electrons 3 and 4 will go in the 2s. And then I go across to the 2p. Fluorine is 1, 2, 3, 4, 5. 2p, 5, done. This is a blast from the past, right? You remember this. I know you do. These are fun. Calcium is number 20. Ca. So I'm going to start with electrons 1 and 2. 1s2. That's it for the first energy level. Electrons 3 and 4 are kind of like lithium and beryllium. 2s2. Then I go across to the 2p. I need all 6. That gets me 10 electrons. I'm going for 20. Next orbital filled is the 3s. You get 2. I go across to the 3p. I need all 6. That gives me 18. 4s. Calcium is the second element. Now a couple things. Let's say it's multiple choice and they say, hey, which of the following is the correct electron configuration for calcium? You could look at the last orbital. Calcium. Calcium on the periodic table should end 4s2. Yep, there it is, 4s2. Another thing you could check, count up these electrons. 2, 4, 10, 12, 18, 20. Element number 20, bingo, calcium. Okay, so let's do some more fun ones. Nickel. Nickel, my buddy nickel, is element number 28. So he's kind of right here. Ni. Not to be confused with nitrogen, it was just N. All right, let's do this. After a while, you realize that they all start out the same way, and it kind of becomes like this awkward chant. 1s2, 2s2, 2p6 gets me 10 electrons. So right now I'm at neon. We got a ways to go. Next row of the periodic table would have the 3s2. I'd hop across to the 3p. I need all 6. Now I'm at 18 argon. All right, here it is. 4s2 gets me to calcium. And now watch. I have it marked in, so I'm never going to get this wrong. When I start filling d orbitals, this is the 3d. Nickel is element 1, 2, 3, 4, 5, 6, 7, 8. 3d8. So again, things that they're going to do to trick you are to say like 4d8. Ooh, tricky, but that's not going to work on you because again, you're smart. That d orbital is always one less than what you might expect. And again, I should be able to count all these. I have 28 electrons. Looks good to me. Okay, so now you may have done these kind of like this when you were in first year chem, which is totally fine. Or you may have done this noble gas shortcut, which is definitely okay in AP as well. If you got something little like fluorine, you might as well just write the electron configuration. That's not a big deal. When the elements get to be a little bit longer, you definitely need to understand this long form that shows all the electrons in all the orbitals. But often, we're most concerned with the outermost electrons, or some of the valence electrons. And if I'm doing bonding or chemical reactions, these inner electrons, or we call them core electrons, they really don't have anything to do with bonding. It's the outermost electrons that I'm most concerned with. The valence electrons give a lot of the properties to a particular element. So if we wanted to shorten this up a little bit, do you remember that noble gas shortcut? You might remember this. The noble gases. Well, I'll put them in here. Helium, and this would be neon, and our friend argon, krypton, and xenon, and radon. So these guys are the noble gases over on the side. Do you remember how you can use the previous noble gas? You put it in brackets, and then you only have to write what comes after that noble gas. So for example, calcium was element number 20. You have to go to the previous noble gas. So the previous noble gas, if I go backwards, would take me to argon. So if you wanted to, you could shorten this up and say argon in brackets. And then you only have to write what comes after argon. Well, again, that saves me 18 electrons. So starting after argon, I'm already at 4s2. So all of this, that's argon. And then I'm just writing the valence electron, argon 4s2. That is 1,000,000% acceptable. Nickel. Again, nickel was number 28. You always have to go backwards. You have to use the previous noble gas. So going backwards, we're looking at argon again. Argon. That saves me the first 18. So all you have to do is write what comes after. 4s2, 3d8. Not bad, huh? Kind of nice. Especially when you get to something like uranium. Element 92. He's down right here. I do not want to write out 92 electrons. No thanks. So we can shorten it up. We go to the previous noble gas. The previous noble gas is going to be, oh nice, radon, Rn. That saves me 86 electrons. Ooh, I like that. Now if you wanted to, you can go crazy and go from 1s2 down to whatever. But not for me. I'm taking the shortcut on this one. Okay, now a couple things. There are two ways that you could write this electron configuration, and both are 1,000,000% acceptable. After argon, I would start at 7s2. That gets me francium and radium, elements 87 and 88. Now, technically, actinium, right here, this is 89. And now this goes to 90, 91, 92. You have one of two options. You could do this. You could go 6D1. That's element 89. And then you could go down here and hit 5F3. This is probably the best way of doing uranium. It seems like if we fill that d orbital, one of the d orbitals, with just one electron, it somehow kind of stabilizes the d orbitals. So that's why you'll notice there's one electron that's up in the d block, and then we go back down to the f block. Now let's say you had something like, oh gosh, I don't know. Let's say just for kicks, you were doing element, oh, I don't know. I kind of like Seaborgium. Seaborgium was named after a scientist called, with his last name Seaborg. He's dead now, but he had this like really cute nose, this giant round nose. He was a cute old guy. Seaborgium, if it's listed on your periodic table, so this is 89. Then it goes, well, this would be like 92. Let's fill this in. 93, 94, 95, 96, 97, 98, 99, 101, 102, 103, 1. Oh, I forgot 100. I was like, wait a second. Okay, 100. Hello, I can count. 101, 102, 103. Here's 104. 105, 106. 06. Element number 106 is Seaborgium, Sg. Oh, for Sg. Okay, let's say I wanted to do Seaborgium. Let's say I'm doing Sg. Element number 106. You could start this the same way. Radon, 7s2. And now if you wanted to, you could go 6d1. Then you'd go back down to the F block for element 90, which would be 5F. It goes across 14. And then technically element 104 is back up in the D block. So then I'm kind of like back to 6D, 1, 2, 3. This would be totally acceptable. If you're following across in your periodic table, this is kind of where your fingers are going to lead you. Or you could do this. Or you could do radon, 7s2. You really could just go 6d4, and then if you went 5f14, they would not mark that wrong. I've asked. Or you could write it like this. They've said either is totally fine. Rn7s2. You could also go like 5f14, 6D4. You could do that too. The chances that they're going to give you one of these elements are very slim because there's so many different ways of writing the electron configuration and they're all acceptable. So I highly doubt they're going to give you anything in this region of the periodic table, but just for your, I don't know, peace of mind, so you could sleep at night, any of these would be 1,000,000% acceptable.